Hello, my name is Abbey Richer. I'm currently in my third year as an undergraduate student at the University of Windsor. For my first formal research project, I will be discussing a laser-based mask characterization for prophylaxis of COVID-19. During the COVID-19 pandemic, face masks have become the new norm with their widespread mandatory use in public. Masking is part of a multi-barrier approach to infection control that includes physical distancing, hand hygiene, and altered social behaviors. Masks provide benefits to both the mask wearer and to those in their proximity, yielding a synergistic protective effect when all individuals in a common area wear them. The effectiveness of masks as part of infection control is premised on ensuring widespread availability, acceptance, and their proper use. The gold standard in personal protective equipment, or PPE, remains the N95 respirator, made of synthetic materials with electrostatic properties that filter and retain more than 95% of aerosols. N95 respirators degrade during washing and disinfection, and as such, are single-use disposable PPE. Owing to their disposable nature, most commercially available PPE, such as the above, are unsustainable for public supply. As a result, the garment industry and a new cottage industry of homemade mask makers have developed to provide fabric face masks to the public. The industry also includes volunteers making donated masks for vulnerable populations. Recently, the US CDC indicated that commercial manufacturers of face masks will require testing, although the conditions of such testing have yet to be outlined. Recently, Dr. Tam has made recommendations for mask materials in an attempt to elevate the quality of masks the public is wearing. However, these recommendations are not easily translatable to actual mask construction, and such recommendations are based on very limited testing of fabric masks. To aid in testing these masks, we are collaborating with a community group that sews masks for widespread distribution to the general public. Ultimately, we can use these results to determine which materials and what construction produces the greatest protection. Fisher et al. Previously presented an effective way of analyzing masks in the paper titled Low-Cost Measurement of Face Mask Efficacy for Filtering Expelled Droplets During Speech. Our group's goals were to emulate these results based on the design system. They modeled a relatively simple configuration as shown in the image to the right. We expected to construct a Mie scattering system for accurate mask analysis. Utilizing the physics present in this project, we concluded that an infrared diode laser would prove to increase the sensitivity while simultaneously decreasing the effect of Rayleigh scattering. We anticipated this would amplify our results as well as lower the cost of the setup, as opposed to the expensive and intense laser used in the Fisher et al. Paper shown on the right. Since our laser of choice operates in the infrared domain, a suitable camera is a Thorlabs camera, which has no infrared filter and will improve detection sensitivity of the scattered light, as opposed to the inexpensive cell phone camera used in Fisher et al. Here's an overhead view of our proposed setup. The camera is recording at a 90-degree viewing angle from the direction of propagation of the laser. The lens and slit are in place to maintain power and collimate the laser beam into the desired shape. The expelled droplets will be recorded once they are incident on the sheet of laser light and become visible to the camera due to the scattering of light. With this geometry, it is essential to maximize the Mie scattering effect at the 90-degree viewing angle. The physics of this project is embedded within Mie scattering theory. It is a type of elastic scattering, meaning the wavelength of the scattered light is the same as that of the incident light. The probability of Mie scattering occurring is independent of wavelength. It is, however, dependent on the size of the scattering particle. As the size increases, scattered light in the forward direction or the direction of propagation increases. The parameters we needed to consider more in depth are the polarization of incident radiation and the angle from which we are viewing the scattered light, which is referred to as the viewing angle. To investigate this, we used a Mie scattering simulator that creates plots based on our experimental parameters. So to the right, based on this log radial graph that plots the calculated scattering intensity from each polarization at different viewing angles, we can see that at our 90-degree viewing angle, which is set by our experimental apparatus, the difference between each polarization is great. To investigate this further, we derived a code in Python to calculate the differential scattering cross-section of polarized light using the Mie Python package mentioned in the Fisher et al. Experiment. We obtained the framework for this code from the website linked below. After careful examination of each variable and how it affects the plot produced, we input the following experimental parameters: the wavelength of incident light, which is 808 nanometers, the refractive index of the particulates being 1.329 to mimic that of water, and various sizes of scattering particles. The input sizes are from as little as 100 nanometers to as large as 1 millimeter to portray the variety of particle sizes that may be viewed coming out of the subject's mouth. There are two identical codes built. However, one is using variables for light polarized in the parallel direction, while the other is using variables for light polarized in the perpendicular direction. Each code created a plot of the differential scattering cross-section as a function of the scattering angle, or rather the viewing angle. Note that the differential scattering cross-section is defined by the probability of the scattering event taking place at some discontinuity. So in our case, that would be a particle. It is evident that as the size of the particle increases, there is increased features and fluctuations on the graph. After examining the average intensities for each polarization, it is clear that perpendicular polarized light consistently produces intensities that are a few orders of magnitude greater than those produced by parallel polarized light. We concluded that perpendicular polarized light would best suit this project, as we want to maximize the collected intensities. Based on these calculations, my colleague Jeremy Marvin has begun constructing such a system in our labs at the University of Windsor. The setup consists of a light-tight box, a thin sheet of laser light about 3 inches in height that passes through a lens to maintain power, shape, and collimate the beam. Then it passes through an adjustable slit into the box until it hits the blocker on the other side of the box. On each of the other sides of the box, there is a hole perpendicular to the sheet of light. We place a Thorlabs camera in one hole that records the droplets expelled from the speaker's mouth that are incident on the sheet of light. And the person wearing one of the test masks speaks into the other hole. So a diode laser is an appropriate choice for this project, since the idea is to measure a large surface area rather than its depth. The diode laser offers a larger beam surface area that we can collimate to the best of our ability in a number of ways to achieve uniform power over the desired area. We used a Thorlabs camera with no infrared filter. It was decided that perpendicular laser polarization would produce the best results. It is also important to note that the viewing angle from the camera's perspective is 90 degrees from the direction of propagation of the laser. We are now just testing aerosols coming from above, which will be shown in the next 2 slides. However, in future trials, the aerosols will come from the side. To obtain our data, the camera records around 20 seconds of video of the emitted aerosols. A code in Python then divides the video into about 200 frames. We run the frames through another code using TrackPy software. This is necessary because the trajectories of individual aerosols can be tracked throughout multiple frames to avoid double counting the same aerosol. The brightness of each particulate relates to the size, as per Millet scattering theory. We recorded and mapped the number of aerosols detected based on the size of each aerosol. By comparing these recorded numbers, we will be able to compare the efficacy of each mask against our control, the N95. To test our apparatus, we used chalk dust particulates and mist from a spray bottle coming from above. On the right is an 18-second clip of chalk dust particulates incident on the sheet of laser light recorded by the camera as a test. From the previous video, we used the TrackPy software to collect and analyze the frames. On the left is the raw frame from the video, and on the right is after running it through the code to track each individual aerosol, which is circled in red. This Millet scattering apparatus cost about $6,000 to build. The goal was to make this as inexpensive as possible. We were successful in observing, recording, and analyzing scattering from aerosols at a 90-degree viewing angle. However, it is still a work in progress as we plan to improve image analysis for detection and sizing, construct a light-tight portable scattering chamber, and to test masks worn by test persons. So at this time, I would like to give thanks to the University of Windsor for supporting the advancement of this project through the Accelerate Grant and the Ignite Grant. I would also like to thank my colleagues, Research Associate Jeremy Marvin, Dr. Ken Drouillard, Dr. Steve Rehse, and Dr. TJ Hammond for their collaboration and support on this project. And thank you all for your attention and consideration.